All right, good afternoon. I'm going to continue talking about EFTs for loosely bound nuclear systems. I'm going to start off by reminding you where we got up to yesterday. So yesterday we computed the leading order interaction for this, the leading order result for this theory, which can be formulated either in terms of a contact interaction between non-relativistic nucleons, or it can be formulated as using a dimer or, excuse me, dibaryon field. And this morning, Professor Kaplan explained how to come up with a subtraction scheme, this sometimes called PDS, in which every diagram in this series has the same order. Just to remind you of that counting, in this particular subtraction scheme, C0 scales like 4 pi over m times mu, and loops scale like mu, actually almost exactly the opposite. If you take the product of a loop and a C0, you get 1. It's designed this way, actually. So then all these graphs are the same size. So that's the idea behind the PDS subtraction scheme, or the one he did by sending IK to IK plus mu. So then it's in this subtraction scheme, it's clear that you have to sum all these graphs and you get a leading order amplitude that's minus 4 pi over m times 1 over a plus IK. The mu dependence goes away when you're done by construction, as it should, because mu is it's a theorist parameter. It's not a piece of experimental data. The mu dependence explicitly cancels between the interaction and the loops. Sure.
Taken a series in which you implemented a subtraction scheme so that all terms are of the same.
Right.
Why couldn't you do something better, that the next term is smaller?
So I don't think you can do that because, yeah, I don't think you can do that and still wind up with a unitary amplitude. Because if you only sum a finite number of these graphs, you don't have this structure that is mandated by the requirement that the S matrix be unitary. Let me say it again in a slightly different way, right? So along with these mu m over 4 pi's come plus IKs. And if you only sum this series to a finite order, these only ever appear in the numerator, and you are restoring unitarity perturbatively, just as you do in phi to the 4th theory or chiral perturbation theory. So in order to get the fully unitary result, you need to sum the bubble to all orders. Or, equivalently, you need to solve the Lippmann-Schwinger equation for this potential. And both of these are guaranteed to generate a result that obeys, S dagger S equals 1. Or in this, you could think about this as if I check the optical theorem for this, it's going to work. Okay. I'm going to redo and then maybe go beyond a little bit what Professor Kaplan talked about in terms of the corrections to this. So a comment here that I think I made yesterday, but I will reiterate, is that this amplitude possesses only low energy scales. So the hierarchy of scales here is that the on-shell momentum K, 2 pi over the de Broglie wavelength, lambda, and the inverse scattering lengths are both small compared to the breakdown scale. And we think this breakdown scale is of order 1 over the range. And we talked a little bit yesterday about the distinction between the effective range and the range of the potential. But this is there's a generic, so all the EFTs I know that are, let's say, healthy, have no information on the ultraviolet scale and the leading order amplitude. Right, so let me say it a slightly different way. So the leading order in the EFT is going to include only long distance physics. And since you don't have any information on the size of the next order correction, you actually have no information here on what the high energy scale is. So if you just compute leading order in an EFT, if you only have that one order, it's essentially impossible to figure out what the breakdown scale is. In order to see the impact of the high energy scale on observables, we need to compute some corrections. So as was already explained, here the ultraviolet physics of finite range enters through, just as it does in the standard model, it enters through higher dimensional operators. So in the standard model, dimension 5 operators, dimension 6, dimension 7 suppressed by 1 over lambda BSM. Here we're going to have an operator that's higher dimensional that encodes the physics of the range. So the one that Dr. Kaplan wrote down is this one, the 2 derivative operator. And this thing here is designed to generate the relative momentum between the 2 nucleons. So since they have equal mass, the relative momentum is just that. But there's another possibility. Which makes the calculation a little bit simpler. Another possibility is that we put in an operator involving time derivatives. I think someone brought this up the other day. And because on shell, we have this relation that this K is equal to the square root of twice the reduced mass times the energy. This operator and this operator are equivalent on shell. So you can think about this as using the equation of motion to convert this operator, which goes like the relative momentum squared, into this operator, which goes like m times the energy. You certainly don't need to carry both of them around because you can trade one for the other using the equation of motion. So in fact, here I'm going to consider, if I was being strict about this, which I guess I should be, I would consider, I always have trouble spelling this. Does Galilean have 3 L's or is it that? Does anyone know? I once gave a whole talk on Galilean invariance at a conference, and at the end, someone came up to me and said, "That was a really great talk, but you misspelled Galilean in the whole talk, right?" So I think it only has 1 L there. It's the distinction between, yeah. But okay, the Galilean invariant combination. So I'm going to C2 over 2 n dagger, and then this operator here is designed explicitly to generate the energy of the pair in their center of mass frame. So this gradient is going to pick up the total momentum of this pair. So this is going to turn into minus once I p squared over 4m, and then this is going to give me, oh, sorry, I don't want the m down here. This is going to give me m times e. So what's the Feynman rule associated with this? the Feynman rule associated with this is I have some minus I because it's always I times the Lagrangian. There's a minus sign. I didn't tell you this is an interaction. So in the Lagrangian, we have a minus sign in front of this. And then I have m times. Where if you think about things in the center of mass frame, the big P is 0 by definition. So here, this is big P is the total momentum of the pair. And then E is the total energy of the pair. All right. So we're going to consider one insertion of C2. So we could evaluate C2 at tree level, will just give us this. Since adding bubbles doesn't change the order of a graph, we can add an arbitrary number of bubbles before the C2. We can add an arbitrary number of bubbles after C2. Or we could add them both before and after. Okay, so this is generic to calculations in Pionless EFT because the vertex, D0, has order q to the -1 because it scales as 1 over mu, and the loop scale is mu. Whatever you start with, as long as it couples to S waves, you can always dress it with all these bubbles. If it doesn't couple to S waves, then no, because these bubbles are explicitly designed to capture the physics of these low energy poles in the S waves. All right, so if you do the algebra here, on this first line, you get C2 times K squared. On this second line, you get, this here is just going to give me, because I have to sum, 0 bubbles, 1 bubble, 2 bubbles, 3 bubbles. So I sum the geometric series and I get back 1 over A plus IK. And then for this last bubble, the one right before C2, sorry, no. Yeah, okay, we can do that. Sorry. Let me make sure I get my signs right here. Yep. Then when I turn things around, it just same, but in the opposite order. And then there's the one with amplitudes on both sides. And you're probably looking at this thinking, well, that looks kind of ugly, but actually there's a very nice result hiding in here because this thing is actually a perfect square, right? So this is 1, this is, let's call this A times B, this is B times A, and this is A times B times A. So you can write this as 1, you can cancel the 4 pi's. And this is not magic. This is actually physics. This is the physics of the fact that what we really have prepended and appended here is the amputated interacting Green's function, right? So this is G0, G0, VG0, G0, VG0, VG0, blah, blah, blah. So, and then we amputated. But that's, so we have these, if we were working in coordinate space, these would actually generate distorted waves, where the waves on the incoming and the outgoing side are both distorted by the potential C0, and then the operator acts on those distorted waves. So then you combine, now you can go one step further and combine the two things in the round brackets, and you get like that. So then this is, if you remember Dr. Kaplan's lecture this morning, he pointed out that you could I'll come over here, you could how much room do I want? This is okay. You could re-expand the effective range expansion so that you treat this as small and do a geometric series in the ratio of this to the two terms that are order Q. And in that case, you get this leading order amplitude, and then 1 plus a half R0 K squared over, if we really want to be careful, I guess I should put the 4 pi over M out the front. So this is the effective range theory result, re-expanded in powers of R times Q, really. And now we have something that has exactly the structure we need to be the next to leading order term. And if we demand that C2 term give the physical effective range, so matching with, so we'll say matching with star, where star is this equation over here, then tells us that C2 K squared over A squared has to be minus 4 pi RE K squared over 2M. Yeah. Yeah, you're right. Right. So this is, I made a brief remark about this, but maybe it wasn't clear. So this ... is meant to represent arbitrary number of bubbles before the square. Yeah. Yeah, so that would be in here. So then if I take, a lot of bubbles here and then only one bubble on the right-hand side, right? So my statement is that what I have here is like the sum from n equals 0 to infinity of bubbles beforehand, and the sum from m equals 0 to infinity of bubbles afterwards. I agree with you. The C2 insertion can be anywhere. So, okay, so I didn't draw all the diagrams, right? So if we work this out sort of loop by loop, instead of trying to jump here, you would have this, right? And then at 2 loops, you can put the 2 loops on the front. You can put the 2 loops on the back. Or you can put 1 loop on the front and 1 loop on the back. Okay, and then you just keep going. So you can exactly think about this as you write down the bubble sum, and then in each, so 0 bubbles, 1 bubble, 2 bubble, in each of those you put C2 anywhere you can. But my claim is that when you're done, you'll have a geometric series on the front and a geometric series on the back, which you can just sum and get. Exactly, right. You can have 0, 1, 2, 3 bubbles on the front and nothing on the back. You can have the other way around. You can have 0 bubbles on either side, or you can have bubbles, right? Yeah. Okay. All right. So just for fun, let me point out that because there's so many geometric series in this problem, right? The next term in the geometric series is just this term squared. Then this is the statement that the n squared LO corrections are now actually determined by the value of C2. So in other words, if I do 2 insertions of C2, where I have to now think, about all the different ways I can stick 2 C2s into an arbitrary number of bubbles. But if I do that calculation, I will generate something with this structure. And in fact, it's better than that, because after I renormalize C2 to match this term, I will get this term for free. And so the next parameter, the next free parameter doesn't come until n cubed LO. I call it P0 for the shape parameter. Dr. Kaplan called it R1. This should be, yeah, like that. And that comes from, I didn't draw, if I included the 4th order piece of the Taylor expansion of K cotangent delta here, then that generates something like this in the round brackets. And then if you assume this is natural, it means because it has inverse mass dimension 3, then this term is suppressed by 3 powers of K over lambda. This term is suppressed by 2 powers, and this term is suppressed by 1 power. So this is exactly this isn't the only term at this order. There's also a R0 cubed, but this is the first order at which you need anything beyond the scattering length and the effective range. You can see the suppression here. If I do C2, if I want to compare the effects of these different operators in MS, I find that if you just take this is the, sorry, this should be R0. These are the values. This is the value in MS. If I compare this to the C0 MS value we got yesterday, this turns out to be R0 A times K squared over 2. So that means that this effect is, so if we say that A is order 1 over K, or K is order 1 over A, it's the same thing, then this suppression is of order K over lambda, because we say R0 is order 1 over lambda. And again, if you don't, it is true that there are some peculiar aspects of this series in MS. So if you redo this with PDS, then you discover that everything scales with mu. But this conclusion about the extent to which the effects of C2 are suppressed by 1 order still holds. So now we say that the overall amplitude is order Q to the -1. This term is suppressed by 1 power of Q. This term is suppressed by 2 powers of Q, and this term is suppressed by 3 powers of Q. And that's the organization of the series for S waves with a shallow bound state. I think my Siri just thought I was asking her a question. Yeah. Sorry? Very good, yes. What do you think it would look like? She's not talking to you, she's talking to me. So, because I said series. So do you want to have a go at what the operator would look like? Right, so you want to basically, you can either take this to the 4th, or you could take this operator squared. Good, okay. So to finish, so here's the goal, which we have now achieved. This is the calculation as you would do it with a contact operator. I am going to say all of this is actually easier if you just make the dibaryon dynamical, although you need to know what power counting you're going for when you do that. So if I start with the same free Lagrangian for nucleons, but then I give the dibaryon a kinetic term, and I have the same sorts of couplings I had yesterday, then the calculation goes through exactly the way it did yesterday. It's just that now the Feynman rule for the dibaryon, or dimer, so all the Feynman rules are as they were yesterday, but the Feynman rule for the bare D propagator is now that if this thing is propagating with total energy E and total 3 momentum P, then we get I over delta plus this coefficient Y times E minus P squared over 4M. So if we think about, remember the way we did this yesterday was we said we were going to take this propagator and solve the Dyson equation. But then there's nothing about the calculation of this self-energy has changed. So it's still true that the self-energy, for example, in MS as a function of E is minus G squared times IMK over 4 pi. We did that calculation yesterday. And so then if we say, so then the dressed propagator here, this is actually a result I'll use later. The dressed propagator here is I divided by delta plus Y times E plus G squared IMK over 4 pi. And then we get the amplitude A by just attaching these vertices that allow the interpolating field to couple to the nucleons. And so that is, that gives us minus G squared over delta. That was there yesterday. But now we have this YE term. So why are we happy that we have a YE term downstairs? We're happy because E is equal to, we're in the center of mass frame, so E is equal to K squared over M. So we can rewrite this as 1 delta over G squared plus Y K squared over G squared M plus IMK over 4 pi. Yeah. So I have, so this is going to have 2 nucleons annihilate and create a dimer. And this one is going to have the dimer annihilate and create 2 nucleons, right? Because this is meant to be a field of baryon number 2, an interpolating field for the 2-body bound state. Okay, so I don't want to belabor the point here, but if you want to make this match the goal up to, we won't worry about the shape parameter at this stage. If you want to make this match the goal, then you can do that by just picking the parameters associated with the dimer. So this 4 pi delta over G squared is 1 over A, and 4 pi Y over M squared G squared is minus R0 over 2. We're going to reuse these formulae in a few minutes, so I'm going to keep them over there. So what we've done is we've actually recovered the effective range expansion up to second order in the Taylor series for K cotangent delta by formulating the scattering problem as a field theory with a dibaryon or dimer degree of freedom. As was commented yesterday, these two Lagrangians are no longer exactly equivalent because you can't do the Hubbard-Stratonovich transformation exactly once the dimer field is dynamical, but they are equivalent order by order in this R over A expansion, at least up to NLO, I guess up to N squared LO too. All right. Yes. Because I want to get the effective range. Yep. You can think about it that way, right? So one advantage, there are a couple of advantages of doing it this way rather than from insertions of C2. So one advantage is that when you do this, you get the N squared LO result for free. And another advantage is that it's, let's say, easier to interpret what's going on here in terms of corrections to the bound state, as we'll see. The disadvantage, this is especially true if you want to insert this propagator in a three-body problem, is that because the denominator here is second order, it doesn't just have one low energy, it doesn't just have one pole, it has two poles. And the second pole is actually spurious in the sense that it's a high energy pole and so is not a prediction of the EFT. There's another peculiar thing I want to call your attention to. So you can't always, so I sort of snuck in here that I was going to put a coefficient in front of the dimer kinetic energy. So I'm using a non-standard kinetic energy. If you start thinking about the parameters here, you might ask why I needed another parameter because I already have G and delta. So it's not immediately clear why I bothered to put this third parameter into the problem. The scattering length is only, there should be an M here, I think, sorry. The scattering length only cares about the ratio delta over G squared. R0 delta doesn't appear. So in principle, you can tune R0 and delta to get whatever, sorry, you can tune delta and G squared to get whatever R0 and A you want. But it wasn't just overkill. There is a reason that this Y is here. If you look at this expression, and let's say I set Y to 1, then what can you tell me about the sign of R0? It's negative, right? So you cannot describe positive effective range unless you introduce this, unless this dimer field has a wrong sign kinetic energy. So it has, so sometimes people who are better educated in high energy, in quantum field theory than I am, will sometimes say that this is a ghost field, right? And it's absolutely true that if you try to consider the effect of this in higher body processes, it can produce violations of unitarity because it has this wrong sign. But as long as you stick to the two-body system, this wrong sign issue doesn't hurt you. But you should be aware that it's not, while this is very convenient, it has certain pathologies. Now, yeah, sure. Yes. Yes. Yeah, so this is actually, there's been some work on this, right? You could take this and you could rewrite the amplitude as the low energy pole plus other, you basically expand around the low energy pole. So yes, and I will effectively be doing that in about, maybe just before the break. No, then the three-body equations are okay. Then they're okay. So effectively, yeah, because then essentially you're treating, so you have to decide exactly what you want to do. So as we'll see, that next to leading order term changes the residue of the pole. right? So then you have to decide if in the three-body equations you're going to include the residue sort of as a non-perturbative effect, and then you're just going to include the regular pieces away from the pole perturbatively. So different people have tried different combinations of these things, but either way, the three-body equations are well formulated. So yeah. Yep. All right. So this pathology of the theory is actually, it has good physics behind it. So we took a zero range potential, and to describe this problem, like the dimer still only generates interactions at zero distance, even if it propagates in time, it's not propagating in space. And so that means that there is a bound first discovered by Wigner, and then rediscovered by myself and collaborator a while ago, that the effective range has to be less than or equal to twice the range of the interaction. It's actually essentially a causality bound. Like, so the effective range is related to the rate of change of the phase shift with energy. And if you sit down and think about what it means for the incoming wave to traverse a potential of radius r, and then the properties of the scattered wave, basically the scattered wave can't emerge before the incoming wave hits the potential, you can prove that there are certain bounds on the behavior of the phase shift. The phase shift can't change more beyond a certain rate of change. And so this converts into a statement that the effective range should be less than or equal to 2 times r. And so if you try to do things with a zero range potential, you have to cheat somewhere. You can't use energy independent potentials with zero range to describe a finite positive effective range. Okay, so I will say a couple of words about other corrections, and then I'll get us started on processes before the tea break. So yesterday, somebody asked me about P waves and SD mixing. So we now have the tools to talk about the size of those things, because we have ways of estimating how big different corrections are. So let's talk about SD mixing first. So as many of you know, and as someone asked me yesterday about whether rotational invariance was violated, and I said no, but you can mix partial waves. So how big is that effect? So if we think about an operator that mixes S waves and D waves, if I was to call the incoming momentum K here and K prime here, then an operator that will give me S waves in the incoming state but D waves in the outgoing state would be the total spin of the system. And I basically couple so I need this will only work if I have spin 1, so that I have a spin vector, and I can couple the spin tensor of rank 2 to the momentum tensor of rank 2, and then get something that's an overall rotational scalar. I get some structure like this, and this will act on the plane wave state here to project out D wave components. But crucially, it has to have 2 powers of momenta to do that. So this operator goes like, let's say, K squared. Yeah, that's what I was trying to do. Yeah. I'm not quite sure whether I got the 1/3 right, but that's what I'm trying to make this. I'm trying to make this traceless, right? So yeah. Okay, so yeah. So I should give this a different symbol. Let's give it an oval. So now we need to remember that on the S wave side, we have we can put as many bubbles as we want and not change the order. But on the D wave side, that's not true. There is no non-perturbative physics on the D wave side, at least not in the nucleon-nucleon system. So when we consider the impact of this operator, we're going to get the leading order amplitude, A minus 1. We're going to get a factor of k squared, and just for, or k prime squared, the way I drew it, but it's the same thing because it's elastic. And then to Tuhin's question, this structure here is actually going to generate for me some sort of P2 cosine theta, which is what puts me in a D wave, where cos theta is the scattering angle k hat dot k hat prime. You can sort of see, right, this going to be like cos squared theta with minus a third. So that's which is proportional to P2. So, and then there'll be some coefficient, CSD. And so on dimensional grounds, we would expect that you can see if this is going to have the same dimension as A minus 1, then CSD has to carry 2 inverse powers of some momentum scale, and CSD scales like, so we'll assume that that's natural, so CSD scales like 1 over lambda squared. And so we discover that this effect scales like k squared over lambda squared times the leading order effect, A minus 1. So in the effective field theory, as has been mentioned several times, you're supposed to write down all the operators that are consistent with the symmetries. So it's not a question of whether this operator is present or not. It's just a question of how big its effect is. But because this operator has 2 more powers of momentum, and because it only has bubbles on one side, not both sides, it's suppressed by k squared over lambda squared as compared to A minus 1. So it's a N2 LO effect because it has 2 powers of the expansion parameters out the front. Estimating the impact of P waves is easier because there are no S waves involved. But if you're worried that P waves may come in and affect the low energy cross section, they certainly will at some energy and at some level. For the moment, I will claim without proof. I'll explain why this is true towards the end of today or maybe tomorrow, that the vertex, that the P wave that generates a P wave looks like that. Sorry, I keep wanting to use P when I should be using K. So this goes like K squared times P1 of cosine theta, or just cosine theta. So if we, so how do I want to say this? Yeah, maybe I should just go. So then this generates a piece of the amplitude that just, okay, so I should say this. So in order to have the correct mass dimensions, the same mass dimensions as this, see the mass dimensions over there are -1 times the non-relativistic mass, big M. So in order for this to have same dimensions as A minus 1, C1 has to scale like 1 over M, and it also has to scale like something to the 3rd power, so that overall the mass dimension of this thing is, or the momentum dimension is -1. So then, as long as P waves are natural and this C1 coefficient associated with P waves encodes that natural scaling, we would expect that P waves are order k squared over lambda cubed. So that is, yeah, that is suppressed by 3 powers because the leading amplitude is order 1 over k. So the picture we have here is that the leading order amplitude is order 1 over momentum. Effective range corrections appear here at where they're suppressed by 1 power of the small parameter. Effective range corrections squared appear here, as does SD mixing in the spin 1 channel, and then P waves and the shape parameter here occur here at N3 LO. And all of this you can get, once you have leading order figured out, the rest is relatively straightforward because everything other than the S waves is just naive dimensional analysis. If you want to do it, you can just do it from the mass dimension of the operator, sorry, the momentum dimension of the operator. Yeah. You're saying, why can't I do? Because I can't, because the D waves are not perturbative. Sorry, are not non-perturbative. So I don't have any, so if we'll talk about loops in P waves, and loops in D waves are in a sense even worse, but loops in D waves are going to have more powers of momentum inside them. So they're going to go like higher powers of momentum. All right. So let me finish off by, since I have the dimer propagator over here, I'm going to work out what its pole is and what its residue is. Before I do that, are there any questions? Then we'll use the pole and the residue after the break to do some processes. All right. Okay, so for those of you who enjoy a bit of quantum field theory, what we are computing here is some Fourier transform, actually a four-dimensional Fourier transform because we have the propagator as a function of E and P of the correlator when we create a dimer at some point and annihilate it at a different point. So there's nothing too fancy about this dimer propagator. It really is just the standard propagator that you'd write down in a quantum field theory, for which you would do something like this. So this, let me go back to leading order and we'll talk about NLO sometime in the second hour. So at leading order, I'm going to set the, let's say another useful feature of having a Y in this expression is I can just say we're going to set Y to 0 because we want to think about leading order. The dimer propagator is I divided by G squared. And then I have, so I'm going to recast, I'm going to trade delta over G squared for M over 4 pi A. And then I have plus I G squared M over 4 pi. Sorry, no. Okay. Now, now I'm going to reintroduce some notation I used yesterday. I'm going to switch from 1 over K to gamma. Because as Dr. Kaplan explained yesterday, and I will repeat here, this object has a pole when K is equal to I gamma. And gamma is in leading order just 1 over A. We'll figure out the next leading order corrections to this after the break. So that's fine, that's all well and good. But if we want this dimer field to be an object that creates a state of unit norm, we're going to have to do wave function renormalization. So to do that, we need to figure out the residue of this object at the pole. So what is that? So to do that it's really just algebra. So I dropped my I, didn't I? Sorry. So we have I times 4 pi over M G squared. And then we want the propagator not as a function of momentum, but as a function of energy. So I'm going to replace K by the square root of ME. I'll replace gamma by the square root of MB, where B is the energy at which the pole occurs. And then I never remember what this is called. If these were square roots, I'd call this rationalizing the denominator, but I multiply top and bottom by the square root of MB minus I times the square root of ME. And then by pulling out a factor of M, I have what I seek. I have an expression in which I have a numerator and I have the pole downstairs as just E plus B. And then we can do exactly what was suggested earlier. We can take the numerator and we can write the numerator as I times 4 pi. We can, at the pole, E is equal to minus B. And so this factor upstairs at the pole becomes 2 times gamma. And then the rest of the terms here are regular in E. So what does this tell us? This tells us that the wave function renormalization for this dimer field is 8 pi gamma over m squared g squared. And this is another result I'll be using after the break. So that means that we can compute processes where photons or weak currents couple to the deuteron using this dimer approach. But when we're finished, we need to multiply the amplitude by the wave function renormalization. So we compute the result for that process with a physical dimer field and not one that doesn't have the correct norm. So we're going to need this factor it actually is related to what you would need to normalize the wave function of the two-body state to 1. That factor is actually 2 gamma. So this turns out to be 4 pi over m squared g squared times what you would think of as the norm of the wave function in quantum mechanics. All right. Yes, I will stop there and I will ask if there are any questions. Sure. Yes. Oh, because I want a time-ordered product. It's a vacuum expectation value of a time-ordered product of fields. This is what I want if I want to compute a Green's function. I need the time-ordered product so that this is actually a Green's function for the dimer equation of motion. Actually, you're probably right. I probably don't need it, right? Because I have to, this one only has creation and this one only has annihilation. So you're right. It's overkill. Thank you. Yeah. Okay. And so this will only be non-zero for x greater than 0. Because the annihilation has to happen after the creation. Other questions? No? Sure. I mean, yes, you can. So I think you know, based on the way you asked your question, I think you know that you can also introduce a trimer field. And then, look for poles of the three-body amplitude by looking for poles of the trimer correlator. There's nothing to stop you keeping on doing this. What happens is that these Green's functions that appear in the self-energy become increasingly complicated. So even here, if we had charged constituents, then the self-energy bubbles wouldn't have the free Green's function in them, they'd have the Coulomb Green's function in them. So if you think about computing a dimer for, let's say, like the bound state of helium-4 and helium-3, they're both charged. Then here, since they're charged, you can also have an infinite number of Coulomb exchanges. And so it's the same deal, 0, 1, 2, 3, 4 Coulomb exchanges in the bubble. So then in the self-energy, you don't just integrate 1 over E plus minus P squared over M, you integrate the Coulomb Green's function. And if you have the three-body system, the Green's function that appears in the trimer self-energy, as you probably know, includes all the ladder diagrams, whatever you want to call them, which I'll talk about those on Thursday, right? So yeah. But you can absolutely do it. I would just say it's not as, if there are long-range interactions in the problem, then the self-energy it takes a little more work to compute. Yeah. Yes, that's all I was, so yeah. So I identified this as ZD. So I want to think about the behavior of the propagator near the bound state pole. And so I want to do a Laurent expansion, and I'm going to argue that near the bound state pole, it looks like ZD divided by E plus B. So for a non-relativistic particle in its center of mass frame, that's the form of the, yeah, that's the pole. The pole is in the energy. Right, so yeah. So this is the analog of computing, you know, of writing your relativistic propagator as Z over P squared minus M squared after you do mass renormalization or something, right? Yep. Yes.
Suppose if I now shift from perturbability to non-perturbability, can I use the same tree, or there will be power, the power will be changed for the non-perturbability?
I mean, you can, I don't exactly know what you mean by what are you non-perturbative in? Yes. Yes.
So, but if I consider the N2LO or NLO, whatever, non-perturbability, that means I can insert as many as I.
You want to resum the range corrections. That's fine, but then, so the first problem is that then, so that can be useful as a quick way to get the N2LO result, but you don't have a power counting that justifies that unless you assume that the effective range is also large, right? Right. So, and if you really wanted to justify this dimer, that's what the dynamical dimer, that is what you would have to do. You'd have to assume that the effective range is also unnaturally enhanced. And then you would conclude that this is the form of the amplitude that you want at leading order. So, but then, as I said, right, then you have some tricky aspects of that theory. Right. Break time? Yeah. Okay. Thank you all. I will see you when. So when do you want to start again? $15 minutes? Yeah, I think we were supposed to start at 4 o'clock. Next one. 4:20, okay.